All right, so hello everybody. It's my pleasure to introduce today's speaker, which is Professor Dwight Barkley. So I should say also this is a joint seminar today between AFMS and the Shear Flows series. So Professor Barkley received his PhD from the University of Texas at Austin. He is a fellow of APS and SIAM, and was awarded the J.D. Crawford Prize in 2005. Without much further ado, I'll leave it to you, Dwight, to start your seminar. Thank you.
Okay, thank you. And thank you very much for the kind invitation. You'll notice there's a slight change in the title from, I think the original title had Universality in the Route to Turbulence or some such thing. I really want to focus more on the broader aspect of the spatial temporal aspects of the route to turbulence in wall-bounded shear flows. And I think I will advertise now and maybe again at the end the talk next week by Bjorn Hoff, which will follow on perhaps naturally from some of the things that I'll discuss today. All right, so let me just start with some broad statements for those that are not familiar with this problem, and that is that in the past approximately 20 years, let's say, there's really been a profound change in our understanding of the route to turbulence in wall-bounded shear flows and how to understand them precisely and correctly, and to understand that it's really a spatial temporal problem and not strictly a temporal problem. And this is what I'm going to explain. And I thought it would be useful to begin with a little bit of history and background, particularly for those who are not at all in the field. And I'm going to go back and discuss a little bit the classical route to turbulence and go back to papers from the 1940s by Landau and Hoff, who first gave some ideas about how flows go from a laminar state to a turbulent state, how you can get turbulence out of a laminar flow. And very similar ideas were expressed, and there's words on here which you can try and read or not. But the idea is that in both cases that there are a sequence of instabilities or transitions, and each instability at some set of parameter values, each instability brings in a new frequency into the problem, and that after a large number of instabilities, potentially infinitely many kind of transitions, they could cascade, that you arrive at a temporally complex state composed of many, possibly infinitely many frequencies, so high dimensional quasi-periodicity, and which would give you a broad power spectrum. And these were really quite profound and important ideas, and there's a lot of other ideas about phase space and how you understand turbulence from a mathematical point of view in this work. You'll notice that I also list Stewart here, Trevor Stewart, because Landau, while he intuited how nonlinearity would manifest itself at these transitions, he intuited the correct answer. It was only Trevor Stewart who first did this correctly and understood the interaction between nonlinearity and the mean flow to give rise to this. So I thought I would mention that as well. Anyway, so we had this notion, which then needed some correction or more sophistication, which came along later in the 70s with the notion that the chaos was important and that you didn't just have quasi-periodicity, but you could have broad range of frequencies even without having infinitely many instabilities, and the notion of strange attractors and so forth. In particular, the work of Ruel and Hawkins, who made, again, the connection to turbulence and dynamical systems. And again, I'm not going to explain this in detail, but just the notion of chaos. And also around the same time, the idea that there'd be universality in dynamics and dynamical systems, which was really caught a lot of people, caught the world by surprise, Mitch Feigenbaum's work. And that, again, here we again see, again, I'm not going to explain this in detail, people would probably be familiar with period doubling, but again, you see sequence of instabilities and that there'll be universality in these, which is independent of any details of any particular system. So all of these things kind of came together, and then I think culminated in these experiments by Golub and Swinney in the 1970s, in which they looked at Taylor-Colette flows. So what you're seeing here are visualizations of Taylor-Colette flows. So it's concentric cylinders, and in this case, the inner cylinder is being rotated and the outer cylinder is fixed. And as you increase the rotation rate of the inner cylinder, that is to say, increase the Reynolds number of the flow, you go through a sequence of transitions. The initial state where you just have a Colette flow, a featureless Colette flow is not shown here, but you get an instability to Taylor cells, and then you increase the Reynolds number further, and then you introduce a first time dependence, and then a second time dependence, and then you begin to get a turbulence, okay? So this was very, very, at the time, revolutionary and very, very influential work on how flows go from being laminar to turbulent. And of course, different flows will exhibit different scenarios in detail. If you do Rayleigh-Bernard convection or flow past the cylinder, you'll see different scenarios, but the basic idea is the same, which is that there's some set of transition sequences which introduce a new temporal complexity to the flow, and then eventually you arrive at turbulence. Of course, it's debatable, and it was debated at the time, and it's still debatable as to whether this tells you anything about the really high Reynolds number turbulence that one would observe in one of these flows. But at least in terms of answering the question, how you go from laminar flow to turbulence, this was our understanding. Okay. Now the thing is, that's not the scenario that takes place in subcritical shear flows, and that is what I want to tell you about. And so that's what's going to be the topic of the talk. And so let me first say that what happens in these subcritical shear flows is turbulence appears abruptly without the appearance of a linear instability of laminar flow to begin with. Hence, the flows are bistable, and the important thing I want to emphasize is they're highly nonlinear right from the onset, and I'll come back and emphasize this several times. And let me just show you, I think everybody here will know what a subcritical transition is here, but let me just show you a simple analog or simple example that I'll find very convenient. So this is a tape measure with a ball stuck to it, so to provide a little bit of additional weight. And the control parameter is the length of the tape measure. And I want you to think of this, this state here is laminar flow. And I get this laminar state, this unperturbed state for a range of control parameters, the length of the rod. But beyond a certain length, there's a second state available to it, a nonlinear state, which I want you to think of analogous to turbulence, which is available. And I can transition back and forth between those two. And if I decrease the Reynolds number, the control parameter a little bit, I still have both states available. I have the highly nonlinear state, and then I have the thing corresponding to laminar. And then if I reduce the control parameter further, again, so low Reynolds, you think of this as low Reynolds number, then I have just the single state available to the system, which again, it users should think of as laminar flow. So this is a very simple analog that people can understand well. And if I were to plot the amplitude, that's to say the deviation from the straight state as a function of the control parameter, the length of it, I would have a bifurcation diagram that is nominally as shown here. This is just a sketch, of course. And I have this. So the main thing is I have two equilibrium. I have this straight equilibrium here, which is going to exist for all values of the control parameter, or at least all the values that I'm going to be concerned with. And then beyond some certain point, I have a second equilibrium, a highly nonlinear equilibrium that's also available to the system. And while it won't be so important in my case, but there's also a threshold, there's an unstable equilibrium that exists between these two, which you can, if you get out your tape measure, you can kind of play around with it and try and find that unstable equilibrium. Okay. And so subcritical shear flows have normally this behavior. And again, this is just a qualitative sketch of this. So I have, again, amplitude is just some measure of the distance from laminar state. So I have laminar flow, which will exist either for all Reynolds numbers or all the Reynolds numbers I'm going to be concerned about. It's linearly stable state, but simultaneously appearing with that is turbulence. It first appears at order, Reynolds number order 1000. It depends exactly how on the particular flow and how Reynolds number is defined, but typically think of it on the order of 1000. The situation is more complicated than I illustrated here, but this is the main features that I want to emphasize. Okay, so that's one thing, is the appearance of a highly nonlinear turbulence without the an instability of the basic laminar state. So that's one of the two properties I want you to know about. And the second is that when turbulence first appears, it appears in a highly intermittent form with spatial temporal complexity on a range of scales, both space and time scales. And this has really been known for a long time, although the importance was not appreciated. These are sketches of mine, but they're based on observations of Reynolds from the 19th century. So what you're seeing here is flow through a pipe. Hopefully these sketches are relatively familiar. This is meant to indicate a diode line. So at low values of the Reynolds number or flow rate, the flow is laminar. For high values, you will find the turbulent state almost invariably. But in between the two, you will find an intermittent mixture of turbulent and laminar, which was originally thought to be dominated by noise, but we now understand to be an intrinsic state of the system. And let me just indicate that, because I will use this word without thinking about it, so that I wanted to just define it right away, is that one of these little localized patches of turbulence that one finds in pipe flow and other flows, one typically refers to as a puff. So I will tend to use that word. Okay. So I'm going to show here, and I'm not going to explain these in detail, just going to show some complexity in a variety of wall-bounded shear flows. And what you're seeing is turbulent and laminar flow. And again, I won't explain it, but you have an a mixture of turbulent and laminar flow that you observe kind of at transitional Reynolds numbers where turbulence first begins to appear in the system. And let me emphasize, let me just show you here. This is a picture of Plain-Couette flow, and I think I can, I have my camera on, and hopefully you can see this. I made here a little Plain-Couette device of about the aspect ratio of this experiment by Prigent et al. And so there's a plate here. There's one plate on one side going to the right or left. I can't tell which way you see it. And the other plate on the other side moving the other direction. So there's a shear. And in between is a fluid. See, is the blue here, that's the fluid. And this is about the aspect ratio of this experiment, just to indicate its large scale. So the distance between the plates is very, very small compared to the size. And this is what you're seeing here. You're seeing the view from this perspective. The walls are clear, and you're seeing into the flow, and you're seeing this is the turbulent part, and this is the laminar, and you see these nice oblique stripes. And there's a lot of discussion of these oblique stripes, which I won't discuss here. This is a movie by Duguay, Schlatter, and Henningsen of the same, roughly the same geometry and the same situation as that experiment by Duguay et al. And you see the formation of these oblique stripe patterns. Let me show you a simulation by Matt Chantry of a stress-free version of this. I'll describe this more later. And here, black is the turbulent region, and white is laminar flow. And what I wanted to emphasize, two things. One is that there's this intermittent mixture of the two, and that it is complex. There's a spatial temporal complexity of this flow, and yeah, let me leave it at that. So. Okay, so that's what we have to describe. So this is invariably observed when you look at these wall-bounded shear flows in the transitional regime where you're in between turbulent and laminar flow. You see turbulent laminar intermittency in this complex spatial temporal form. Okay, so this is then what we have. We have, at low Reynolds number, we definitely have laminar flow. That's the only state available to the system. At high Reynolds number, we have turbulent flow. It may coexist with laminar, it may coexist bistably with laminar flow, but turbulence will be the preferred state in that it doesn't take much noise or perturbation to the system to give rise to turbulence. And certainly once you get turbulence, it will invade everywhere and you have a fully turbulent flow. But between those two, if you look carefully, you'll find this intermittent spatial temporal complexity. And almost invariably, this is the case. And I would like to organize it this way for purposes of discussion. So I'm now going to plot on this axis turbulent fraction. So in laminar flow, by definition, the fraction or the proportion of the flow that is turbulent is 0. And in fully turbulent flow, the proportion of the flow that is turbulent is 1. So it's all turbulent. And then in this intermittent region, if you take a space-time average, you will have a turbulent fraction that is someplace between 0 and 1. And I show it here varying continuously between 0 and 1, and that's kind of important. So there are two things I'm going to tell you about for the rest of the talk. One is I want to talk about this point here, which is really the organizing center and why everything happens. That is to say, why is it that when you have something that's fully turbulent, why does intermittency appear in the first place in these flows? I want to discuss that. And it's really the organizing center, and it really has to do with fronts and the problem. And then the other thing, which was the original title of the talk, which has to do with universality, and this is where a lot of the attention has been focused in recent years in understanding precisely this point, and that there are well-defined critical points in these subcritical shear flows where the turbulence fraction does continuously increase from zero, and we have an understanding now, a pretty good, clear understanding of how that works. So those are the 2 points I'm going to now discuss. Okay, and I seem to be doing well on time. Okay, so let me take the first, let me just say something because I thought of it now and I'll probably forget to say it later, is as far as I know, as far as we understand, there is no universality associated. This is not a hard transition. There's no critical point here that we know how to define, at least currently, whereas this point we do. So, but let me go ahead nevertheless and start with this. And having explained this many times, I've learned that this is the way to do it. So I first have to tell you about 2 players in the problem, and these are called puffs and slugs. And so I want you imagine the following situation. I'm going to do this in pipe flow, but similar things, they're more complicated, but similar things exist in other well-bounded shear flows. So I'm going to imagine an inlet to the pipe, and I'm going to perturb it. So I have a fully developed laminar flow, and I'm going to perturb it some way so as to generate turbulence. And I'm going to ask what happens in a spatial temporal context. And so depending on the Reynolds number, I'll see one of 2 things. So at a real transitional Reynolds number, which you should think of 2000. 2000 is a very, is transitional Reynolds number in pipe flow. And if I look as a function of space down the axis and time, what you'll find is that perturbation remains as a localized perturbation, which is one of these puffs, which I already mentioned very early on in the talk. So you have a localized, and it doesn't spread upstream or down. It moves downstream, it's affected by the flow downstream, but it doesn't spread out spatially. Okay, so you have a localized state of puff. If you do the same nominal experiment, but at higher Reynolds number, say 5,000, what will happen is that patch of turbulence that you injected into the flow will spread it, and there will be an upstream front and a downstream front, and they'll move at different speeds, and the turbulence within the system will expand. And this is known as a slug, and it's expanding bit of turbulence. Okay. And just to emphasize, I'm going to say this a lot, is that what's really going to be important is this, the 2 fronts, the upstream and the downstream front, are going to be crucial players in this story. Okay, let me just show some experiments and numerical simulations. In particular, this gives me an opportunity to highlight work out of Tom Mullen's lab. So I'm going to show some movies by Tom Mullen and George Pexino. Tom was very instrumental in a lot of this early work on the problem. So what you're seeing is pipe flow at Reynolds number 1,900, very close to 2,000. And I'm going to show down below a numerical simulation by Mark Avila at the same Reynolds number. And you see one of these puffs. You see it's a localized structure. It's moving down the pipe. We very often will look at a co-moving frame of reference that you're seeing here. You see it is more or less a fixed structure in this moving frame of reference. And it doesn't expand. It doesn't contract. It is dynamically complex. You could argue whether that's really turbulent or not, and those of us who work in transition call that turbulence. I mean, it's not high Reynolds number turbulence, but nevertheless it is complex, temporally complex behavior. But anyway, it's this localized patch, and that's one of mine, and that's the puff. I wanted to just show you that. Just to show you one final thing, again, these are now time-space diagrams, but they show essentially the same thing from the work of Nishi et al. And again, you see at low Reynolds numbers, transitional Reynolds numbers, you see the localized puff, which maintains its form. It doesn't spread upstream or downstream. You'll notice the asymmetry, and I'll get onto this, between the 2 sides of the puff. And then at higher Reynolds number, you see the expanding slug. And again, I want to emphasize that you have these fronts, or these interfaces between the turbulent and laminar flow, which are going to be quite important. Okay, so now I've led you to this already, which is that these the fronts between turbulent and laminar flow are really quite important in these spatial temporal problems, because I have a mixture of turbulent and laminar flow, and what's important is the fronts between these. And this has been widely recognized for a very long time. I just give some key papers here, but there are many others. In particular, Don Coles clearly stated all of this in 1961, the importance of the interfaces between turbulent and laminar flow. very important work on pipe flow that many of you will know with Nansky and Champagne, some seminal work on understanding pipe flow, the puffs and slugs in pipe flow. And again, the notion that it's the interfaces between the laminar and turbulent flow, which are really the crucial objects here. And so what we want to understand is we imagine we have laminar flow and turbulent flow in different regions, and we have a front, a relatively sharp front connecting these. And so again, these two mechanical equilibria, I have one corresponding to laminar flow, one corresponding to turbulent flow, and then there's going to be some region of space in which I connect these in some way. And just to really emphasize this, and hopefully you won't find this too corny, I put 4 tape measures down and showed this. And the thing that I really want to emphasize, again, I've said this, but I'm going to keep saying it, is, again, this corresponds to the turbulent state, and this is the laminar state. And these are highly separated. I mean, that is, as mechanical equilibria, these are very, very distinct. And the small parameter is not the distance of the turbulent flow from the laminar flow, but potentially is the sharpness of the interface. You can use that as a small parameter, but the small parameter is not the strength of the turbulence. Anyway, I just want to emphasize that. So as I say, this is not new. This has been widely known, and many of you will own a copy of Landau and Lifshitz. And I invite you to go get out Landau and Lifshitz and find the description of pipe flow, and you will find in words, in about 2 or 3 paragraphs, what I'm now going to tell you. So it was understood that that there's a fronts between turbulent and laminar flow, and those are important. It's written down in this book and my copies from the 1950s. They didn't write down any equations, but Yves Pommeau did, and it's the same ideas. And this isn't Yves' notation, but it's what was being said. And the idea is to understand generically what would happen if I connected laminar flow and turbulent flow through a front. And let me just show you this. And the question is, what way does that front move? So you have a front connecting these two, and what does it do? And it's going to move, and you'd like to understand how does it move. And I'll just say, how does it move relative to the mean flow of this? And what is described in Landau and Lifshitz is the following, is that turbulence, so we assume turbulence can exist, and the front will move depending on whether turbulence is favored or not. So you imagine that there's a free energy. So this is turbulence and this is free energy, and I have a local minimum corresponding to laminar flow and a local minimum of the free energy corresponding to turbulence. And if turbulence exists as a minimum but is not energetically favored, then the front will contract. That is to say, laminar flow will be favored, and a patch of turbulence will contract. If turbulence is the favored state, it has a lower free energy, the turbulence will expand and take over the flow. So that's what you would have. That would be the classical description of a hard transition, okay, of a hard transition in a spatial context. The spatial temporal context is that you would have well, that's just, let me just say that. That's the description you would have, okay? So the problem with it is it doesn't describe what we see, and particularly it misses the intermittency, which we now know to be so crucial to transition. So this is a simulation by Bofang Song. He started turbulent pipe flow at a relatively high Reynolds number, and he dropped the Reynolds number into the intermittent regime. And what you see is that the turbulence, rather than just disappearing, it forms this intermittent pattern of these turbulent puffs. Now, this gives a slightly misleading representation. It looks almost as if though they appear periodically. They won't in general appear periodically. They can be arbitrary distances between these. They can appear in quite spatially complex form. Okay, but nevertheless, you will have these localized puffs. And that is what is missing from this Landau-Lifshitz Pommeau theory of transition. They simply cannot describe these, and yet we know that they're crucial. Okay, so let me now describe to you how this actually works. And so I'm going to look at a slug, a relatively high Reynolds number, and again, this is from simulations of Bofang Song. And I want you, this is a snapshot, but I want you to imagine looking this in a co-moving frame of reference in which this upstream front here is stationary. And it is stationary, of course, in this snapshot. So upstream of this front, I have laminar flow, fully developed laminar flow. And I want you to think of this fully developed laminar flow as like fuel. So there's a lot of kinetic energy in this laminar flow. It's a parabolic profile. Kinetic energy goes as the square of the velocity. So there's a lot of kinetic energy in there. So relative to the stationary front, this laminar flow is flowing into that front. And what has happened is there's a rapid conversion of this laminar kinetic energy into turbulent kinetic energy. The kinetic energy budget, the kinetic energy production greatly exceeds the dissipation in this region. As a result, you blunt the shear profile. Okay, that is to say, you've extracted energy from the shear profile. As a result, you've blunted it. You've taken energy out of it. And then downstream of this front, you then reach an equilibrium where production is balanced by dissipation. And this is just what we call turbulent pipe flow, and that's our second equilibrium. So let me just say, upstream, you have the one mechanical equilibrium corresponding to one state of the tape measure. And downstream of this front, you have the other mechanical equilibrium corresponding to this balance between production and dissipation. Okay, and this state of turbulent flow, again, is well understood, very well studied. I'm sure there are many people who know a lot about this and a lot more about this than I do. I'll just mention my colleague Joe Klowicki, who really can tell you a whole lot about how this balance works and how the nature of this mean shear profile. Okay, and one of the ways I'd like you to think about this is that again, in this frame of reference in which this front is stationary, what we see is upstream here there is no turbulent kinetic energy entering this control volume. Just think of this as one large control volume. There is no turbulent kinetic energy entering this control volume, but there is turbulent kinetic energy exiting that control volume. Where that turbulent energy comes from, turbulent kinetic energy comes from, is from this front, and only from this front. Here they're in balance. The production is balanced by dissipation. There's no net change in turbulent kinetic energy here. It all comes from this front, where production exceeds dissipation. Okay, so that's where it's produced in this control volume. And also, by the way, let's just leave it at that. So I have these, again, these two mechanical equilibria connected by this front. Now I want you to imagine the situation in which I decrease the Reynolds number. That is to say, I increase the dissipation. I've told you from the beginning, eventually I will lose the second mechanical equilibrium that exists, and it will just disappear. However, what happens in this flow is that does disappear, but what persists is this front where production exceeded dissipation. That will persist through the loss of this second equilibrium. And so what happens now is I still have where production exceeds dissipation. I still have that front. I blunt the shear profile, but once I blunt the shear profile, turbulence can no longer be sustained in the presence of that blunted shear profile. So in fact, what happens is dissipation exceeds production, the turbulent kinetic energy dissipates. Once the turbulent kinetic energy is gone, the shear profile reaccelerates and I'm back to laminar flow. So in this case, I have incoming laminar flow, I have an exiting laminar flow with no net increase in turbulent kinetic energy because it's produced and then it dissipates. Okay, and that is what a puff is. So from this, we can really understand clearly what one of these localized states is. It's a front continually burning laminar flow and leaving behind no downstream turbulent wake. And something that's important for the full story here, but I won't really make a point of it, is that there is this refractory region behind the puff where you have to reaccelerate the shear profile before you can excite another one. So there must be a gap here between patches of turbulence. Let me pay attention to my time. Okay, and then I believe, having said that, I believe now if you look at this movie, you can see this. I can certainly see this with my eye. Unfortunately, I don't have the laminar, the mean profile to show on here, but I believe you can see that what is happening is in one of these turbulent patches is it's burning laminar kinetic energy, turning it into turbulence, and then dissipates. That laminar profile then reaccelerates, and then you can re-energize another puff. Here, let me restart the movie. You can then re-energize another puff, dissipate it. It burns laminar kinetic energy. You can then re-accelerate, etc. And so turbulence is sustained in this spatially intermittent form. So even though if you tried to fill this pipe with turbulence, you could not sustain a turbulence in that form. It is not a stable equilibrium of the system. Fully turbulent pipe flow is not stable at this Reynolds number. However, it can sustain itself through this intermittent form because you can reaccelerate the flow in between these turbulent patches. There's no turbulent dissipation in these laminar gaps. You can reaccelerate the flow in those gaps. And I'm just going to show this. This is a Bunsen burner. The air fuel mixture is flowing up. I think we all know that what's happening is the flame front is moving down. Actually, it's moving perpendicular here, but the net direction is downwards. It's flowing into the air fuel mixture. And I just invite you to think of it this way. And the reason I want to emphasize this is that the front motion is into the dominant mean flow of the system. And the reason I want to emphasize that is that it explains just very naturally and intuitively the well-known observation that the turbulence in these shear flows moves at a slower rate than the mean flow, and it's because the front motion is against the mean flow. So you can actually, to stay on time, I think I'm more or less going to skip this. Let me just say that those were all pictures and so forth. I mean, obviously we've done more, and I say by we, I mean Bofang Song has done a lot of analysis of this. And just to say these are different states in space-time plots. These are different slug states and a puff state. And just to show you that the upstream front of the slug evolves as a function of Reynolds number and becomes the puff state. And you can see this in the kinetic energy budgets that you have upstream and downstream fronts. There's a lot of details here I don't want to get into, but you have this equilibrium, and these aren't just sketches on here. These are the actual equilibrium that are measured between production and dissipation that exists in the core of these slugs, which you then lose, but you still have a puff which corresponds to the continuation of this upstream front. Okay, so I think I've gotten that idea across. So the thing is that we must account for this. We must account for the mean shear in our description. So we have two equilibria. What I wanted to tell you is that we have two equilibria. We have a laminar state, and we have a turbulent state. We have fronts between those. But in order to describe this correctly, and what was missing from what Landau and Lifshitz and Yves Pomeau and other people said, was that the fact is that this mean shear profile plays an important role in the dynamics at transition. It's probably not so important at very high Reynolds number, but in the transitional regime, this really is a crucial player. Okay, now I've described this in a number of papers with colleagues, and I'll just let you read about that. I'm going to give you a brief idea. Maybe you can hear this, maybe you can. That's a heartbeat. I think you're very familiar with the general idea of this. So I also work on electrophysiology, and so I knew about this. And what you're hearing with your ear there is blood pumping. But what you're seeing here is electrocardiogram, which is measuring the electrical activity in the heart, and you're familiar with these pictures. And what I want to emphasize is that these are really very, very closely related to puffs in pipe flow. That is to say, you have a large amplitude excitation followed by a refractory period in which the system can't be excited, followed by another large amplitude excitation and then a refractory period in which the system cannot be excited. And that is the same mechanism by which action potentials in neurons work. It's the same electrophysiology with, I mean, minor differences, or depending on your field, you might call them major differences, but the idea is essentially the same. So the thing is this mechanism by which your heart communicates electrically, or your brain works, the action potentials in your brain, that is an extremely robust, highly nonlinear, highly spatial temporal mechanism. Okay, there's no such thing as a fixed action potential down a neuron. An action potential by which you think has to be moving. Okay, these electrical waves in the heart have to move. They have to, they're spatial temporal by necessity. So anyway, I worked on these, and so I knew about this, and so I can recognize the connection between this and what you see in pipe flow. And what's important is what the community who works on these kind of models recognized long ago from the 1950s is that you can learn a whole lot by considering generic features and simple polynomial nonlinearities, that these are highly complex phenomena. I mean, the electrophysiology here is very, very complex, but you can learn a lot simply by looking at simple polynomial nonlinearities. And so that's what I've done, and I'm going to explain this very quickly. And I'll just let you read about the details. So what I'm going to show now is simple, this is really just a generalization of what Landau and Lifshitz and E. Pomoe said to include the mean shear. That's all that I'm doing. But I now have two variables. I have the mean shear and turbulence. So I'm going to plot little phase portraits here. This is a turbulent level, that's 0, and this is some non-zero turbulence. And U here, so that's the turbulent intensity. And U is, you can think of it as center line velocity, but I want you to think of the physical variable as the state of the shear profile. Okay, so those are my two variables. And just to orient you, this here would correspond to the fully developed laminar flow. So the turbulence is 0, and the center line velocity is its maximum value. Okay, and so I have two kinds of dynamics. I have the dynamics of the shear profile, or the centerline velocity, if you want to think of it. And what it is such that if you have turbulence, that the shear profile blunts. So you decrease the shear profile. And in the absence of turbulence, it increases. That's all you need to know about that. And for the turbulent dynamics, all I'm simply going to use the simple cubic nonlinearity as, again, Landau, what's written in Landau and Lifshitz essentially, which is that you have my two stable states. I have a laminar stable state and a turbulent stable state, and they're separated by a threshold. The only difference that I've added now is that there's also the state of the shear profile affects that, okay? But nevertheless, just two stable states separated by an unstable equilibrium. Then I need the effective Reynolds number. What Reynolds number will do is we'll push that as a function of shear profile, we'll push it to in the direction shown. And let me just put it all together and you'll understand. So any place where the red curve and the blue curve intersect, I have an equilibrium for the full system. So this equilibrium here corresponds to fully developed laminar flow, and it exists as a stable equilibrium of the system. So the turbulence is 0 and the laminar profile is fully developed. Okay, as I increase Reynolds number, what happens is I will develop a second crossing or a second equilibrium of the flow, a stable equilibrium, and that corresponds to fully developed turbulent flow, and it's a stable equilibrium. So those are the two, my two equilibrium, the laminar equilibrium and the turbulent equilibrium. The two equilibrium I've been discussing since the beginning of this talk. Pay attention to my time. You have to add some spatial effects. You have to add downstream advection and diffusive coupling, but let me not worry about those. So this is the message I want you to get across. And let me just do this by showing you the connection of these phase portraits to the things I've been showing you. And let me start with a slug. So I've showed you, I discussed this slug, and now I have a phase portrait and I want to show you the connection between them. So we're just going to, what I'm going to do is go back and describe this slug as a function of space going from upstream to downstream. So what happens is downstream, I have this laminar flow, which corresponds to this fixed point here in this two-dimensional phase space. The turbulence is 0, and I have my centerline velocity is at its maximum. That is this case here. I go through this front, okay, and what happens is the turbulence increases, and as a result, following that, the shear profile blunts, and I have a blunted shear profile, and that's what I've indicated here. I don't know if you can see that blunted profile, but the shear profile blunts, it becomes, it's decreased relative to the laminar flow. And then I reach an equilibrium between these two, and that is this, the core of the turbulence flow, okay? It's simply a generic picture of what I've described here. This is real DNS, and this is just a generic picture, but it describes that state, okay? So I transition between my two equilibria through a front that undergoes this transition, okay? And again, then I can describe what happens as I lower the Reynolds number. As I lower the Reynolds number, I get this puff state. And again, as I go through in space, I have this fully developed laminar flow upstream. I then go through this front, the turbulence increases, and as a result, I extract energy, and the turbulent and the shear profile blunts. And that's this blunting of the shear profile here. Unlike in the slug case, I no longer have this equilibrium. This equilibrium has disappeared from the system, okay? I've lost this equilibrium that existed here. It no longer exists. And so what happens is once the shear profile blunts, I then return to my, the turbulence then decays. And the turbulence decays here, you can see it in this DNS. The turbulence decays, and after following that, downstream, the shear profile reaccelerates, and that's what's indicated here, the shear profile reaccelerates. So that is the difference between a slug and a puff in terms of these phase portraits of turbulent kinetic energy as a function of centerline velocity, or you can think of it as the state of the shear profile. And these have names. This would be referred to as the excitable state, so I can excite the turbulence, but it doesn't exist as an equilibrium itself, or this bistable where the turbulence exists as an equilibrium. And let me just say, I hadn't thought to say this, but again, so when you say, oh, but this does exist, it exists and it persists. It persists because it's constantly, what it's really doing is moving upstream. What it's constantly doing is re-exciting turbulent, it's re-exciting laminar, constantly converting laminar kinetic energy into turbulent kinetic energy. That's how it exists, right? This equilibrium exists as an equilibrium in the absence of a front. This can only exist as a front, okay, very much the way an action potential does. Right, let me better go on. So this then is what I want you to think about. I have excitable state, bistable. To have a full kind of theory for this, you have to take into account that the turbulent branch, the turbulent state, is itself a highly fluctuating state. And you can do that either with deterministic chaos or multiplicative noise, and I won't describe that here. So I better just, I'm just going to kind of whip through just a few things here just to give you an idea, and then I'm going to go on to the next topic. And that is that, we, or that is to say, Bofang Song has looked at this, and again, in real DNS of pipe flow and kind of verified these ideas. Also, Rinaldi and all have looked at this in curved pipes and seen how this scenario plays out if you slightly curve a pipe, and how this plays out. I'll just let you read about those papers if you're interested. I'll also just say that, and maybe I kind of hope Bjorn talks about this next week as a little pressure. I'm not going to, just to say that one can look at the speeds of the fronts in puffs and slugs and understand them in this way. And all I want to say about this is, well, there are two things I want to say about this. One is that so this is speeds of the interfaces of puffs and slugs as a function of Reynolds number. And I want to just emphasize that if you looked at the Landau, Lifshitz, Pommeau kind of ideas, that what you would get is this upper branch here, and this is the solution or the description that you would get. And it works okay at high Reynolds number. It does, again, give you the correct idea, but it doesn't really describe correctly what happens at transitional Reynolds number. It misses important features. Whereas these ideas, you can reproduce the flow more or less exactly. And then I'm just going to really just highlight here that these ideas, I want to say two things about this. What you're seeing, now let me explain what you're seeing. What you're seeing here is a panel. There are 3 panels here, and in each case, on the left-hand side, you're seeing reality, where reality is defined as either direct numerical simulation or experiments or both. And what you're seeing in the right-hand portion of each panel is the model results. And just to say that in terms of large-scale phenomena, this modeling, this transition between excitability and bistability seems to capture essentially all the large-scale phenomena that people care about in the transitional community. And there's a lot of things that people care about in the transitional community. So let me go on. So I've now spent most of the time talking about this. Why do these flows become intermittent at all? And they become intermittent because you lose this equilibrium, the second equilibrium of the flow, but you don't lose it. You don't lose the turbulence when you lose that equilibrium. It becomes this intermittent form, this excitable media kind of form of turbulence. What I want to now discuss is what has received a whole lot of attention in recent years, is this critical point where turbulence eventually, you can either view it eventually, you lose turbulence as you decrease Reynolds number, or turbulence first appears as you increase Reynolds number, okay? And the universality associated with that. Okay, so this brings me to statistical phase transitions. And so this, again, dates back to the early 1980s by work by Janssen and Grasberger, who proposed that there was a kind of universality in a variety of systems, heterogeneous chemical reactions, or forest fires, or flow through porous media, or flu epidemics, as we now are all very much aware of. And what they, I'll just quote from Grasberger's paper, that suggested another type of universality comprising all critical points with an absorbing state in a single order parameter. Now, I'm not going to describe this in great detail, but I do want to say something about the kind of universality that appears here. Okay, And just to say that at around the same time, or just shortly thereafter, Kaninko and Pomot made the connection between spatial temporal complexity, in Kaninko's case, spatial temporal intermittency in coupled map lattices, and Yves Pomot specifically in the hydrodynamic context, that these kind of things, the kind of things that Janssen and Grasberger were discussing, would appear potentially in hydrodynamic problems. And we went on to be able to see the universality that was being proposed in these problems. And it took an incredibly long time to resolve this, and it's because the space and time scales are so large. I'll get to that in a minute. But let me just give you just a highlight of what generically we're talking about. So what you're going to see here are space-time plots. And there's going to be the active state, which in our particular case is the turbulence, and it will show up as black. And there's going to be the absorbing state, which is the generic turb, which in our case is a laminar flow, and it's white. Okay, and you're going to see for two values of the controlling parameter, and this is just going to be generic. The controlling parameter is a ratio of the spreading rate versus decay rate. And now that well, I'll come back to that in a minute. What you're actually going to, what I'm actually going to simulate is a coupled map lattice, and that doesn't really matter unless you're an expert. And so I'm going to start in both cases with an initial seed, one at small values of this parameter and one at large values. And what you see is that for small values, there is spreading, that there is turbulence or active state persisting in the system for a certain amount of time, but then eventually you reach the laminar state. And once you're in the laminar state, as I've told you, laminar flow is linearly stable. You will never come back. You will remain laminar for all time. Whereas if you go to a larger value of R, the control parameter, the turbulent state will persist in an intermittent fashion for arbitrarily large time. And of course, we're all very familiar with that because of the ongoing pandemic, this idea that there be a ratio of a spreading rate to a decay rate being a controlling parameter, and that you have something like a disease that is spreading around and people get it. But if the spreading rate is sufficiently low, which is what obviously we would like to happen now through a vaccination program, that if that R value is less than 1, or approximately 1, then the infection will die down. And if you remove the infection entirely from the population, then it won't come back. If it's really, really removed, it will never come back. Whereas if you're above that, then you get an epidemic, and then you have this complex spatial temporal passing around of the infection. Okay, so this now is very easy. I used to have to spend a lot of time explaining this, but now it's, of course, it's in the popular cultures. So I'm now going to show you another case where I'll speed this up, where I've now smaller steps in the control parameter. And unfortunately, I may have to go back and replay that so that it goes all the way to the end there. Smaller steps in the control parameter, and I've now started with turbulence everywhere in the system. But nevertheless, what this shows is that there is, in the limit of, so as I now take smaller values of the control parameter, there is in fact a critical point distinguishing when the turbulence dies and when the turbulence doesn't. And you have to take a thermodynamic limit here. You have to make the system increasingly large as you get close to this critical value. And you have to take increasingly large times for you to be able to see this. But nevertheless, there is a well-defined sharp critical point separating these two cases. That below this, that if you wait long enough, you will definitely, the turbulence with probability 1 will die, and it won't persist infinite time. Whereas above that critical point, at least if you go into this thermodynamic limit of large space and large time, that with probability 1, the turbulence will live indefinitely. Okay, so that's understood, and that does give you a well-defined critical point. And if you look carefully, what you can see is that the turbulent fraction increases as a function of this control parameter from this critical point. So what you have to do is, it's statistical. You have to take averages. You have to take space-time averages. After some transient period, you have to take space-time averages, and you see that the amount of turbulence, the amount of black, turbulent fraction is increasing as a function of Reynolds number. And that happens, that growth in turbulent fraction as a function of Reynolds number occurs with an exponent beta in a universal way. And I'll say a little bit more about that in a minute. Okay, but it does increase continuously from 0. There are other critical exponents associated with this, and they have to do with the sparsity of the patterns. And you can see that there's a divergence of scales as you move towards this critical Reynolds number, that the gaps here, the laminar gaps here are increasing in scale. And there's a gap associated with in the spatial directions and gaps associated in the laminar directions. And these are increasing as you approach criticality here. And so they have corresponding negative exponents, one parallel to the time direction and one perpendicular to the time direction. And together we then have three critical scalings, one associated with the turbulent fraction and two associated with the characteristic space and time scales. And from these critical exponents, any other exponent can be obtained. And the thing is, and what Janssen and Grasberger proposed, is that these exponents are independent of precise details of the system, that the same exponents that would apply to epidemics would apply to turbulent shear flows, is the idea. That they only depend on the dimensionality of the system. They don't depend in any way on the specific details. They do depend on the dimensionality of the system. And to be clear, back to my plane Colette flow. So this is a plane Colette flow. This is what we call a two-dimensional system. It's real three-dimensional flow. There's fluid in there. It's real a turbulent flow. It's three-dimensional flow. But we call this two-dimensional because it has two large dimensions and one very small dimension, which we, okay, so it's two large dimensions. So then there have been a number of papers on this, and I'm not going to describe them. I'm only going to describe one, which is the work we did, and well, I say we, I really mean Matt Chantry did. And it's what we call Wallet flow. It's like plane Colette flow, but with stress-free boundaries. And by using stress-free boundaries and a body force, you can go to extremely large systems. And let me just show that here. What you're seeing here in this blue, that was the largest numerical simulation that had been done to date. And this is the largest experiment that had been done to date when Matt did these simulations. And this is one of these turbulent laminar intermittent patterns. And what Matt was able to do by going to this stress-free case is to go to extremely large system sizes, which I show here. And the point is that you need to go to large system sizes if you want to look at these sparse patterns and to look at the scaling. And that's just the same thing here. And let me just show you, I'm going to show you now a movie. I'm just going to encapsulate very briefly what Matt saw. So what I'm going to plot here is turbulent fraction as a function of time, both on logarithmic scales. And I'm going to show you three simulations. This one here is below the critical Reynolds number. This one here is above the critical Reynolds number. And this one is very, very close to the critical Reynolds number. So this one, ultimately, the turbulence is going to decay. And let me just say, the actual simulation is only 1/4 of the size here. Matt, these are very expensive. Matt did not want to spend a lot of time simulating the decay to laminar flow. So it's 1/4 of the domain repeated. This is going to saturate, and this is going to decay very, very slowly. So what you're seeing now is turbulent fraction is a function of time for each of the three cases. The green is this case, the red is this case, and the blue is, oh shoot, sorry, play that again, is that case. The dashed line there is the universal exponent that you would expect to see based on these percolation ideas. Okay, based on the Janssen-Grasberger. And what you're going to see then is what I just described. The green is going to decay. You're below the critical Reynolds number, only slightly below. It's going to persist for a long time. Experts in the field should appreciate that the time scales here, that's over 10 to the 5 time units. Eventually, this red one saturates. Again, it statistically saturates at some finite turbulent fraction. The blue here is decaying slowly, very slowly along according to this universal characteristic. It will either eventually fully decay or saturate at some very low value. And just to say, through a lot of very, very hard work, Matt was able to verify the three scaling exponents, one associated with the temporal characteristics, one associated with the spatial characteristics, and one associated with the turbulent fraction. And what one finds then is that there is a well-defined critical point for this flow in which there's an onset of turbulence, and the turbulent fraction really does grow continuously from zero. And it's a direct confirmation of the directed percolation universality in a planar shear flow. And this requires a little bit more discussion, and I'm going to discuss it in my conclusion, which I'll get to in just a minute. So I wanted to discuss this a little bit more. Before that, I just want to just one slide on ongoing work. And there's a lot of ongoing work in this field, but let me just highlight a couple of things. One is just generally about plane channel flow, which a number of groups are looking at. And I apologize if you're working on this and I haven't included you here. But there's an interesting regime in which you kind of have a one-sided state, and the way percolation plays out in that context is something people are looking at. And I'll just mention a graduate student, Sebastian Gomez has looked at, is also looking at this, and I'll go on to say that one of the things that Sebastian is looking at, and it was in my abstract, but I just decided it's too preliminary, and I'm not going to talk about it here, is that these flows are dominated by extremely rare events and extreme value statistics, and he's working on numerical methods and analysis of understanding those events. And I'll just say for some future talk, either I or he can tell you about that. And also that we're also looking at some interesting effects of Lagrangian tracers in such flows. And that's with Akhilesh Verma, postdoc, working with us. So then in the last minutes, let me conclude here, give some concluding remarks and tell you what I've told you. So this is the overall overview. So I talked about two things, sort of the mechanism giving rise to intermittency, which is really kind of crucial to just describing all these phenomena, and the other is the universal critical point. So let me just say what I described here. And that is that, again, what we're looking at in these subcritical shear flows is we have two equilibria that are competing. We have a laminar state and a turbulent state. And those are somehow in competition with fronts between those. And what I've told you is to really understand that and to understand the transition problem is that you have to realize that what you go from is that when you lose this bistability, when you lose that second equilibrium, that upper branch equilibrium, it doesn't mean you lose fully access to it, that you go into an excitable state instead. And that really dictates what happens in this intermittent regime where a lot of the interest is taking place. And then when you add fluctuations to that picture, you really gain the essential organizing center for the transition in many wall-bounded shear flows. And then it's fundamentally, I would say, it's a transition between this bistable state and this excitable state is where the upper branch is turbulent, is really the key thing. And again, I've said this several times, but I want to say it again, is that this is a strongly nonlinear mechanism. That if there's a small parameter in the system, the small parameter is this sharpness of the interfaces, not the closeness of laminar flow to turbulent. That remains, for all values for all parameters we care about here, you have a strongly nonlinear system, okay? But this is a strongly nonlinear system and is highly robust, and it dictates the spatial temporal dynamics of the onset. And then the second thing I want to say and get back to what I started with is that this involves then a paradigm shift. So we have this kind of you could view as classical idea of transition to turbulence or route to turbulence, and which does take place in many shear flows and many situations where you go from laminar flow to turbulence through a sequence of transitions, each introducing a kind of new temporal complexity corresponding to some spatial structure, but not super large scale spatial structure. And the ideas of bifurcation analysis and stability and so forth. And in this case, we often do have small parameters, which is distance from the bifurcation in which to expand about and to understand. And I want to distinguish that from the spatial temporal intermittency that we now come to understand in these wall-bounded shear flows, where you have a statistical transition and that there is no, that you have a highly nonlinear system right from the onset, that there is no small parameter, or if there is a small parameter, it's the sharpness in the interface between the black and the white. Okay, but we nevertheless do have in these systems, and again, this took us a long time to really fully understand, we do have continuous transitions in systems in which there's bistability. And that, again, seems like a contradiction, but we now understand it to be the case. And again, I want to come back, and then this will be my final thing, is to summarize what these simulations from Matt Chantry. These are actually DNS from Matt Chantry as a function of Reynolds number. And what you see is that, again, for low values of the Reynolds number, the only state accessible to the system is laminar flow. You will eventually always end up at laminar flow. As you increase the Reynolds number, what you'll find is that you can have turbulence, and turbulence will persist, and will persist in this highly intermittent spatial temporal complex state. Okay, but if you were to look at any patch of this turbulence, you would see turbulence that didn't look so much different from the turbulence here at slightly higher Reynolds number. Okay, the turbulence exists, it just exists in this intermittent form, and it grows continuously. The turbulent fraction grows continuously from zero. It grows continuously from zero, or let's do it this way, by going down. The turbulent fraction goes to zero, not because the level of turbulence goes to zero, but because turbulence becomes sparse. Okay, and that's the way you should think about it. and it becomes sparse in a universal way. It obeys a universal scaling in the way it becomes sparseness. And so this has brought tremendous clarity in the field to our understanding of how wall-bounded shear flows become turbulent. And it really, and in addition to that, is we have this, these beautiful confirmations of these universal scaling laws that were predicted many years ago. And with that, I'll conclude and just acknowledge the work of many colleagues and collaborators who I've discussed this with over the years and have contributed to the work. And I apologize if I didn't cite everybody's work in this talk. Many people have worked on this. And I also want to support, acknowledge support from the Simons Foundation. And with that, I'll end and take questions. Thank you.
Hi, Dwight. Thank you so much for that talk. That was fantastic. We do have time for questions if people want to stick around. Oh, we already have a question from Joe. Go ahead and unmute and ask it, Joe, if you like.
Hi, Dwight. That was really good. So just one comment and then a sort of a quick question, I guess. The one comment is what you described looks in terms of the puffs where they, grow and then die and then grow and then die. It kind of reminds me of, for example, slope flow, a stratified slope flow, where you get turbulence, then there's mixing and it kills the buoyancy mechanism, and then it relaminarizes and then does it again.
Oh, okay, let's talk about that. Okay,
yeah,
great.
So that really looks a lot like what you have here, it sort of puts its own fire out. And then the second question I have is when you get close to the fully turbulent case, does the wall come into play at all? So you're mixing momentum, and so you're driving that momentum that's near the center line toward the wall, and now you're driving a strong shear near the wall. Does at some point the production generated by the high shear near the wall take over?
Well, it's funny. You're the person I always come to ask these questions. So it's funny that you would be asking me. But I don't think. I mean, it would be really strange to me if it didn't at some point. But yeah, no, I think it does, because that's the equal. That's what you describe, and that is the equal. That is the equilibrium. I think yes. I think the answer is yes.
Okay, so.
Can I just say that?
Yeah, okay, so that's an interesting question, or research question, I guess, as to how that sort of handshake takes place from the transitional mechanism to the fully turbulent mechanism.
There's a lot of things we don't understand about so I said, okay, I early on decided I think I'll just deal with the generic model that catches the essential thing. Is see, the thing is those shear profiles in the intermittent regimes, there's a lot we don't understand about them, but they depend on exactly which streamwise slice you're looking at. So there's a lot of complexity there, and how that eventually then gives rise to that downstream, the kind of shear profile that you're familiar with, and the production that you're familiar with, how you morph from one to the other. I think it's safe to say we haven't mapped that out.
Okay.
I certainly haven't mapped that out, but I don't think anybody has.
Cool. All right. Thanks.
We'll talk later. Yeah, we'll talk later. Thanks.
Great. Thanks, Drew. Other questions from the audience? Feel free to put up the little hand and I can call on you, or just feel free to also unmute and ask. Oh, we have someone with their hand up. Feel free to go ahead and unmute.
Shusong, I think she's for asking.
Yeah.
Oh,
okay.
yes.
Yeah. Very nice talk. Okay. So I have a question about this critical exponents.
Yeah.
So it's very nice to have these universal values. But on the other hand, what's the specific significance in the hydrodynamically here?
Yeah, okay. I think it's fair that you know, I think it's, yeah. I think it's fair. I think that's a fair question. Let me help you out. I don't think it's wrong. Yeah. You could say, what's the point? You know, and I think you can, it's fair to ask that. And the thing is, first of all, it's interesting. Okay, so the thing is, I wanted to state, you know, the fact is it's interesting, but I want to say why, from the people who are really just interested in turbulence, why they should care about this. The thing is, you know, you would really like to ask, I mean, it is a basic question, how you go from laminar flow to turbulent flow as you increase Reynolds number, you know, by what scenario does that play out? Let's not worry so much about the exponents for the moment. Just, you know, you'd like to understand by what scenario that plays out. And the thing is, what was the case prior, you know, let's say certainly 20 years ago, but let's say 15 years ago, is that people would get, there would be a lot of arguments and disagreements and potentially lack of understanding because you don't have the kind of ideal model, the ideal system in mind that you're trying to, that you're aiming for. You also don't understand the incredible significance of system sizes. So what happens is you end up with inability to really, for people, different people to agree on things. And so the significance comes about because you then begin to converge on an idea. I don't think it's worth generating these incredibly large system sizes in very many other flows. I mean, Bjorn, and hopefully Bjorn will talk about this next week. He's done some beautiful experiments, you know, beautiful experiments come out of his labs of looking at this in a couple of different situations. But I think he would agree, he can speak next week for himself, is that it's probably not important to do this very many times, but it is important to do it a few times to know what it is that really exists underlying these things. Yeah, so you would like to, so all right, are these exponents are, you know, statistical physicists love power laws and they love these exponents and they love to know that it's universal. And I think it's worth knowing that in a few cases, these really do play out this way. And there are some, and let me just say some scientific questions about Navier-Stokes is not a local system because pressure globally couples things. So it's not at all obvious that this would fall into the universality class. There's certain technical points there. And it does fall in the universality class and it's a non-trivial statement. I'll just say that. But you care about it because you need to know, at least in a few cases, that it really does play out the way you thought. And then you can probably just say, okay, we now understand, and now we don't have to worry about trying to get real close here to this critical Reynolds number in the scaling. We just see, it's going to be in that case, and then, okay, we're done. I don't know if that answers your question or not, but that's the answer that I would give.
Okay, thank you. If I may I ask another question? The diagram you referred to several times, the bistable and the excitable state. Okay, so here you have, okay, these red lines, I hope they're red, I'm colorblind. These the state representing turbulence, I guess.
Yeah.
Okay, so they are not, okay. Is this a steady state or actually time dependent?
Yeah. Okay. So right.
So what kind of the spatial temporal characteristics of this proxy of turbulence? So
yeah,
to what
right.
extent
Okay, so
they actually mimic turbulence?
Okay. Well, so let me just show you the actual measurements of these. If I can get back to this. I mean, some people have measured these. So what you do is you measure, then you take means. So those would be, so what I would just say is what you're seeing here, here it is. What you're seeing here are, these are actually DNS. So, I mean, this is real.
Yeah, I know, your model problem, yeah,
okay, so the model problem is I'm taking that to be, again, I'm using generic thing. I would say that is, the solid curves are the mean, are meant to mean the mean turbulent kinetic, the mean turbulence intensity, but what actually the system experiences is not just its mean, but the fluctuations about that mean. Both are important. In fact, here you can see it very well. That's the mean, and these are the fluctuations about the mean.
So that does the PDE system describe the spatial, this kind of fairly chaotic, random spatial temporal behaviors?
Okay, well, maybe I don't understand the point of your question. I mean, as you well know, what, let's see if you can see this on my slide. What actually goes on in the turbulence, of course, is many people have looked at that, you know, in detail, the kind of the nature, kind of dynamical systems nature of that state. It's a, you know, and there's these idea, these pinball periodic orbits ideas. Anyway, the point is, there's a lot of interesting dynamics just within that state. I'm not being concerned. I'm really much more concerned about the fronts. So I'm not so concerned about the detailed nature of that. I'm simply saying that there's a mean for it and there's a fluctuation about that mean. And that's all I'm putting into the modeling, and conceptually that's what I'm being concerned with. So I'm ignoring a lot of known properties of the turbulence, of transitional turbulence, in order to get somewhere. In order to be able to describe the front between laminar and turbulent flow. Again, I'm not sure I'm answering.
Okay, I kind of, you know, whether it's, you know, this front is more complex than a hydraulic jump or something like that.
It is more,
maybe
yeah. Well, it is more complex than a hydraulic jump. I mean, maybe, okay.
Yeah, but that's a kind of connection, join the two kind of bias that, I mean, I thought probably it is true that your PDE system actually carries a lot of spatial temporal information, that your turbulence is actually more than just a equilibrium state.
Oh,
you know,
yeah.
The sense of a fixed point.
Yeah, that's right. It does. That's right.
Okay.
All right, I think Hugh has had his hand up for a little while, so sorry. We have time at the end. We can circle back.
Well, I have, yeah. So hi, Dwight. Oh, got a funny background anyway. That doesn't matter. Thanks for the talk. I managed to tear myself away from the class that you see there. I had a kind of mundane question. What is the influence on this? You showed us a lot of outcomes where the universality was apparent you had to make the domain sizes very large. What is the influence on the behavior, or if you reduce the domain size? So can you, with things you can probably afford to do, what can you learn about this behavior in a domain that's maybe too small, and how do you know? Can you learn anything in a domain that's too small other than that you can capture the fully turbulent state maybe? Yeah, that'll do. I'll mute myself. Let me go
come on to this one. So the thing is, what will happen is so these are finite sized domains, and let's say that this, or something not too much smaller than this, is not so difficult to access nowadays. Well, actually, let me do it this way. Let me put this up. What will happen is, is if you have a finite domain, what you'll do is basically you'll cut this off at some scale. And if you want to think about it, there's some turbulence fraction below which you cannot access because some, this much turbulence in this system corresponds to a certain turbulent fraction, right? You agree? That percentage of turbulence in this corresponds to some value on here. And if your system is small, you simply cannot access these low values of turbulent fraction. They're just not accessible to the system.
Right.
And so, yes, you get cut off, and you may see
the upper part of that.
What?
You're going to see the upper part of that curve only.
You'll see the upper part of that.
You're going to jump from laminar to that upper branch there.
Yeah, that's right. You would jump. You would then see discontinuity. And in fact, for any finite system, you will see a discontinuity. It's just that discontinuity becomes smaller and smaller and smaller as you go to larger and larger system size. There are always, even in Matt's work, there's still going to be a minimum turbulence fraction that he can obtain in the system, and therefore there's going to always be a finite jump. So
that's interesting. Yeah.
The thing is, it's again. Let me just and for everybody just to understand. It is real. My view is it's really important to have looked at some of this universality in some of these systems to really clarify that that's where we are. Obviously, you don't want to, you're not going to do this in every case, but it doesn't prevent the system, nevertheless, from being spatially temporally complex. I mean, even Reynolds knew this. He associated it with noise, but nevertheless, even in Reynolds' experiments from 130 years ago, it was known that that you will observe spatial temporal complexity. So it is important to understand this scenario that you have basically large amplitude turbulence coexisting with laminar state, that plays out in a spatial temporally complex way, and that is the scenario. Let me jump up into this to distinguish. To distinguish these two scenarios. They're really very distinct scenarios. There's some ways in which you can try and meld them together, but they're distinct scenarios. And it's important to understand this, this scenario versus this scenario, even if you're not going to observe the actual critical exponents associated with it. At least the signatures of it will be available to you in kind of moderately sized systems. And it is helpful to be aware of that.
Sure.
And that's
I buy that.
And let me just come back to, that's why in some ways the onset of intermittency is probably, certainly from the fluid dynamics point of view, I'd say the more important point. And just historically, people dating back, people like Coles and Wignansky and so forth, they associated that with the onset of turbulence, was the onset of fully turbulent flow, the onset of the second equilibrium, stable equilibrium where you have fully developed pipe flow. That is what they call the transition problem. And the intermittency that you saw below was some artifact. But anyway, that I would view as really the more fundamental of the two from the fluid dynamics point of view. That loss of that upper branch fixed point and the onset of intermittency is the more fundamental of the two from a fluid mechanics point of view.
Mm-hmm. Okay. Thanks again.
All right. Do we have any other questions from the audience? Okay. So if not, we'll